Hello everyone. We are still talking about the graph algorithms and the shortest path problem. This is the last part of the shortest path, the series of the videos on shortest path problem. And in this one, we are going to focus on all pairs shortest path. We have a graph. So far, the algorithms that we have discussed, both Dijkstra and Bell-Manford, find the single source shortest path problem. Basically, they find the shortest path from a given source node to all other nodes in the graph. The Dijkstra algorithm works over the edges with non-negative weights, over a graph with non-negative edges, and the Bell-Manford algorithm works over a graph with negative edges but without negative cycles. Now our problem is that we wanted to find the shortest path between all the nodes in the graph. How can I actually solve this problem? A naive solution is to, and assuming that the graph can have negative edges but not negative cycles. Be careful. If there is any negative cycle in your graph, the shortest path problem cannot be solved. So the naive solution here is to just run the Bell-Manford algorithm for all the nodes in the graph. The cost of the Bell-Manford algorithm, we already know that the cost of the Bell-Manford algorithm is n of m, right? N is the number of edges, and the number of vertices, and m is the number of edges. And if we run it over all the nodes in the graph, the cost is going to be O of n power 2m, okay? But the thing is, m, the number of edges itself, can be O of n power 2. So in total, this can be reached to O of n4, which is basically very high. So we wanted to see that is it possible to get anything better than n power 4, finding the shortest path for all the edges in the graph, for all the nodes in all the pairs of nodes in the graph, in the time complexity less than n power 4. Is it possible to solve it? And the answer is yes. And again, we are going to use dynamic programming. So the idea of finding the shortest path between all the pairs kind of is very similar to the Bell-Manford algorithm. This is again a dynamic programming algorithm, but there is one main difference between this one and the Bell-Manford. In the Bell-Manford algorithm, basically we were looking for the single source. So we were looking for the distance from one single node S to all other nodes. So we put a constraint over the number of edges that you can use to reach from the node S to any node V. Remember? And we defined D of V and I, where I was the number of edges that you use. Number of edges. Okay, the number of arcs. The reason was that S is fixed, right? So we are just, actually S is fixed, and in this table, I just need to represent V, the other side of the node, different actually nodes for V, and the number of edges. In the case of finding the shortest path between all the pairs, our sub-problems will be way more than this, because S can be also variable, right? So one thing that I should know that here, when I'm actually defining the table. The table basically is going to cover, you should actually think about it as U and V, where U is just the distance from U to V, the distance from U to V. And we have to also think about, so U is the starting point, V is the final point, starting from U reaching to V. But basically here, if I use the number of edges as a part of the actually counters for the subproblem, this is going to give me a lot of different subproblems. The reason is that if I put the constraint, I know that there is a constraint over the edges, but just a constraint over the edges is not going to be enough, because U and V, both of them are variable. When you are thinking about which edges you can use, the number of edges that you can use can be completely variant, and you don't know that which edges you are using. Okay, so I'm just trying to tell you that the subproblems that we are going to define for the reoccurrence here again have this constraint over the number of edges, but I'm going to rewrite that constraint in a different way. I'm going to rewrite it using the number of edges. Okay, so I am going to define D of I and J and K to be all of these I, J, and K will be vertices. Just referring to the vertices, I'm not going to refer to the edges anymore. I'm going to refer to the nodes, to the vertices. This is going to tell me that what is the shortest distance from I to J using the vertices from number 1 to K. Just give some some label to all the vertices, and you can only use the vertices from 1 to K. You can see that this is basically just putting a constraint over the number of edges implicitly as well. But instead of directly working over the edges, because the total number of edges is going to be n power 2, right? This is correct that you can use at most n1 minus 1 number of edges, but which n minus 1 number of edges among all the edges here? This is going to make the problem much harder if you are going to work over the edges. Instead of that, I am going to work over the vertices. So I don't care that how many vertices have been used here. What I care is that you can only use K number of, you can only use the vertices from 1 to K. Okay, it doesn't mean that you are using K number of edges, but it's just forcing you to use only this number of vertices. You cannot use the other vertices. If I actually show it to you over some example, I'm sure that's going to be more clear. But let's just think about the reoccurrence relation. The base case for this reoccurrence relation is D of I and J, where you are not using any other nodes as intermediate node. Okay, so it is telling you that D of I and J and 0 will be equal to infinity if there is no edge between I and J. But if there is an edge between I and J, so basically it's just that 0 tells you that you are not allowed to use any other node to reach from I to J. If this is 1, for example, I, J, and 1, d of I, j, and 1, it tells you that you can only use one node, and that node is going to be the node number 1. Okay, you are not allowed to use any other node. So you should either go from I to j using a direct edge, or you can go from I to 1 and then from 1 to j. So basically this is telling me that this is going to be either d of I, j, and 0, so without any additional node, or using from I to the node 1, don't use any other node, plus d of one and j using no other nodes. Okay, so, or for example, just one more step of it, d of I, j, and 2. This will be either just use the node 1, so I, j, and 1, or you can actually then use the node 2 as well. So in that case, it will be d of I and the node 2 using the node 1 plus d of going from the node 2 to j. Again, you can use the node 1. Okay, so it actually gives you a lot of options here, that you can go to this one, and then this one, or you can go to this one, and then this one, or you can actually just go directly using this one or this one. Okay, so it is basically the full reoccurrence relation. I'm just again trying to explain it one more time from scratch. So d of I and j, d of I, j, and k basically tells you what is the shortest path from I to j. So shortest length, shortest path, distance from I to j using the nodes from 1 to k, not other nodes. And again, just assume that you give a label to all the nodes. So when k is 0, it means that you are not allowed to use any other edge, right? So you are not allowed to use any other node. Basically, there should be an edge between I and j. If there is no edge between I and j, the cost will be infinite. If there is an edge, the cost will be the cost of that edge. When you are using any value greater than 1 for k, greater than 0 for k, for example, for k plus 1, you can either use it using d of I and j and k. So basically you are just telling me that, okay, I don't want to use the node number k plus 1. So this is I, this is j, and I already know what is the path. This is the path using k, the nodes from 1 to k. Okay, and just assume that this is a new node k plus 1. Okay, so the cost of d of I and j and k plus 1 is the cost of going from I to this node, and then going from this node to J. How? In this path, you can only use the nodes between 1 and K, and in this path, again, you can only use the nodes between 1 and K. Okay, so this is the distance from I to the node K plus 1, from I to the node K plus 1, using the nodes from 1 to K, and the path from the node K plus 1 to J, using the nodes 1 to K. So these two are basically just exactly showing these two. This one and this one. So you can either don't use the vertex number K plus 1 and just go from the previous value of D of I and J and K, or you can use the node number K plus 1. Okay, so this recursive relationship that I showed you here can be implemented in this way. I mean, the implementation, I think, is very easy. Just probably it is the case that you didn't get the idea yet. Let me actually just explain the algorithm. That at first we initialize D of I and J with 0 for all the edges of I and J that we have for V. We initialize all of them as infinite. For everyone that, for all the edges that we have, we change the cost, the distance, from I to J, using 0 number of edges to be the cost of all those edges I and J. And then I need 3 loops, right? One loop that iterates over K. You can see that I have 3 dimension in my recursive relation. So for each one, I need a loop. The first loop is going to iterate over K. This loop is iterate for I, and this loop is iterate for J. So for D of I and J and K plus 1, this is going to just coming from the minimum of this one and the minimum of the summation of this, the minimum of this one and this summation. Okay, just keep this relationship in mind. Let me just use this one. I'm going to copy this one and put it over the example that I'm going to show you. Before leaving that, the time complexity here is clearly O of n power 3. This is definitely better than running the Bellman-Ford algorithm. The Bellman-Ford algorithm for n times. That's going to be O of n power 2m, which is definitely worse than this O of n power 3. So this is going to find the shortest distance. This exercise is just asking you to update the algorithm to find the shortest path as well. Basically, for finding the shortest path, what you need is you need an array for the parent, right? But this time the array is not going to be a single, one-dimension array. You need to define it as a 2-dimensional array. So P of I and J, you would actually just update it with K plus 1 whenever you get the solution from this one, right? So whenever you get the solution from this part, you update P of I and J to be the node K plus 1. That's basically, you just need to keep all those parenting information, but for all the pairs, not just for one node. So just assume that we have a graph like this one, we wanted to run this algorithm, this dynamic programming algorithm that is called Floyd-Warshall. All these names actually just coming from the name of the scientist who introduced, who developed the algorithm. So Floyd-Warshall, two persons who developed these algorithms. So this is you can see that the table has 3 dimensions. That's why I am showing it as just 2-dimension tables, but in total you have n number of 2-dimension tables, right? So this is going to be the table of d of I and j and 0. I have fixed the last dimension to 0, and this is going to be the table. Basically the table just shows all the edges, right? And for the rest of them I just put the infinity. So I am going to fill and actually solve the table of 1, d of I and j and 1. So what we are going to do, I can't. Okay, I'm going to leave this one here. That helped me to actually fill out the table. Okay, we are going to fill this table for all those ones that the column and row are the same. The cost is going to be 0. The cost of going from the node 1 to 2 using 1. This is basically going to be either the cost of going from 1 to 2 using no other edge, the minimum between this one and the other one is this one. This is going to be d of 1 and 1 using no other edge plus d of 1 and 2 and using no other actually cost. So for this case you can see that there are some basically kind of redundancy, but that's okay, the algorithm doesn't really care. The cost here is going to be 6, right, from this table. This one is going to be 0, and this one is going to be again 6. So basically this is going to be 6. Very similar for 3. This actually the 3 is going to be 8 as well. For 4 this is going to be again infinite, because basically this part is going to be four. This is infinite and this is infinite, and that's why it actually keeps it as infinite. And for 5 this is going to be -4. Very similar to the first one, but this one might be actually a little bit different. For 2, okay, d of 2, 1 and 1 will be the minimum of d of 2 and 1 using no other node and the summation of 2 and 1 using no other node plus d of 1 and 1 using no other node. Again, for this one, this is going to be infinite, this is going to be infinite, this is going to be 0, so this is going to be infinite. Not this one, but let's actually just check this one. We are going to check the cost of 2 and 3 using 1. So this is going to be the minimum of cost of 2, 3 using no other node, and 2 and 1 using no other node plus 1 and 3 using no other node. This was infinite, the cost of going from 2 to 3 using no other node. The cost of going from 2 to 1 using no other node is infinite, and the cost of 1 to 3 using no other node was 8, so this one is going to be infinite as well. Now this one is not going to change. How about 4? The cost of going from 2 to 4 using 1, so this is going to be this one, right? This one is going to be infinite as well. I'm not going to write down all the formulas here, but this one is going to be infinite as well. The cost of going from 2 to 5 using only the node 1, this one is going to be infinite as well. Sorry, these are not infinite basically because there is a direct edge from 2 to 4, and there is a direct edge from 2 to 5, which was 7, but later on we might actually get something better. The cost of 3 and 1 using no other nodes, the cost of 3 and 1 using no other nodes plus the cost of 1 and 1 using no other nodes, so this one is going to be infinite as well. How about this node? The cost of going from 3 to 2 using the node 1. Again, this one is not going to be updated. This will be actually 4, because the reason is there is no path from actually 3 to go to 1, because 3 to 1 is infinite already, so definitely this is going to be as whatever we have before. The cost of going from 3 to 4 using the node 1, again this is going to be infinite. The cost of going from 3 to 5 using the node 1, this is going to be infinite. The cost of going from the node 4 to 1, this is going to be 2. There is a direct edge. The cost of going from 4 to node 2 using the node 1, this is exactly where the algorithm is going to show me some difference. So let me just remove this and show you that how the algorithm is going to help to fill this cell. Okay, we are going to fill this cell, right? This is the cost of, we are looking for the cost of going from 4 to 2 using the node 1. This is going to be the minimum between these two cases. Either don't use the node 1, so that's going to be the cost of going from 4 to 2 using 0 other edge. So basically we know that this is infinite, or you are going to actually get the minimum between these two. The cost of going from the node 4 to the node 1 without any other node, plus the cost of going from the node 1 to 2 without using any other node. So these two, both of them are coming from 4 and 1, this one, and 1 and 2, this one, right? The summation of 2 and 4, this is going to be 6. It actually just basically tells you that from 4 go to 1, then go to 2, which basically just coming from this part and this part. Also the cost of going from 4 to 3 using 1. Again, in this case, this is going to be the minimum between the cost of going from 4 to 3 without any other node, or the cost of going from 4 to 1 without other nodes, plus the cost of going 1 to 3 without any other node. Okay, so basically this is telling me to compare this one and this path. This one is -5, this one is 2, this one is 8. This summation here is going to be 10. Of course, -5 is better, so it keeps -5. Okay, and this one is 0. How about this one? The cost of going from 4, this one is also actually nice. I am going to find the cost of going from, the cost of reaching from 4 to 5 using 1. This is going to be either don't use node 1, so this is going to be the cost of reaching from 4 to 5 without any node, or go from 4 to 1 without any node, and then go from 1 to 5 without any node. So basically that's going to be this one plus this one. This is going to be 2 plus -4. This is going to be -2. How about this one? There is no edge directly going from 4 to 5, so this is going to be infinite. Basically, you can see that this is infinite, and I'm actually getting these two exactly from the table. 4 to 1 and 1 to 5. So this one is going to be -2. Nice. And then you actually just calculate for 5 to 1. So let me actually just clean a little bit here. So from this is basically going to be d of 5 and 1 and 0, which is infinite, d of 5, 1 and 0 plus d of 1 and 1 and 0. This one is 0, this one is infinite, and this one is infinite. So basically this one is going to be infinite. But the cost of going from... Now I think all of these ones are going to be infinite anyway. Basically the reason is that you cannot go out of 5 and reach to 1 using just one edge. So all of these ones are going to be infinite. So in total, this is going to be I think I made a mistake. This one is not 8. This one is, sorry, this is not 6. This one is 8. D of 4 and 2 using 1. Yeah, that was 4 and 2 using 1. 2 and 6, that's going to be 8. I just noticed that I made a mistake there. Okay, this is the full tree here, the full table. I'm not going to actually go through the rest of the example, but I have filled the whole table, and you can actually see that how we can fill the table number 2 from table number 3, table number 3, and basically you can see that this is just the last part of it that is changing. The full example is available. Just do it for yourself and see that how it actually keeps updating the table. The last thing that I'm going to emphasize here is that the space complexity of Floyd-Warshall, the way that it actually shows here, is clearly O of n power 3. You have n number of tables. But again, just like the modification that we can do over the Bellman-Ford algorithms, you can see that when you are filling the table number k, you are just using the table number k minus 1. So you don't exactly need O of n power 3 space. Keeping only 2 number of tables at each time is going to be enough, so you can modify it and reach to n power 2 space complexity, but still the time complexity is going to be O of n power 3. This is going to finish this oral discussion over the shortest path problem, which is covered the chapter 24 of the CLRS and 2 sections 4.4 and 4.6 from the DPV.